welcome to our problem walkthrough. Today, we'll explore an exciting problem titled Count Array Pairs Divisible by K. In this session, we'll break down the problem, analyze different approaches, and guide you step by step to the optimal solution. Let's dive in and see how we can solve this together. In this problem, we are given an integer array called nums and another integer k. The task is to determine how many pairs of indices, I, j, exist such that the product of the two numbers at these indices, nums, I, asterisk nums, j, is divisible by k. There are a few constraints to keep in mind. First, the indices I and j must satisfy the condition 0 equals I less than j nums.length, meaning that I must always be less than j. For the input, the array nums contains integers where its size can go up to 100,000 elements, and each element has a value between 1 and 100,000. Similarly, k is also an integer within the range of 1 to 100,000. The output you need to produce is a single integer that represents the total count of valid pairs, I, j, that meet the given conditions. Let's look at the first example to understand this problem better. Here, nums is 2, 3, 4, 6, and k is 6. The output is 4 because there are exactly 4 pairs of indices, I, j, where the product of the numbers at those indices is divisible by k. For instance, one pair is 0, 2, where nums, 0, asterisk nums, 2, equals 2 asterisk 4, which is 8. Since 8 is divisible by 6, this pair is valid. Similarly, the pair 0, 3 gives 2 asterisk 6 which is 12, the pair 1, 3 gives 3 asterisk 6 which is 18, and the pair 2, 3 gives 4 asterisk 6 which is 24. All of these products are divisible by 6, so we count all 4 pairs as valid. The output, therefore, is 4. Now let's consider the second example. Here, nums is 1, 2, 3, 4, and k is 5. In this case, no pair of indices satisfies the condition that the product of nums, I, and nums, j, is divisible by k. For example, the product of any two numbers in nums, whether it's 1 asterisk 2, 1 asterisk 3, or any other combination, does not evenly divide by 5. As a result, the output here is 0 because there are no valid pairs. This example highlights that it's possible to have cases where no pairs meet the condition, and the output should simply reflect that by returning 0. Finally, let's look at the third example. The input array nums is 10, 20, 30, 40, and k is 10. This time, there are 6 valid pairs of indices, I, j, where the product of the numbers at those indices is divisible by 10. To illustrate, the pair 0, 1 corresponds to 10 asterisk 20, which is 200 and divisible by 10. Similarly, the pairs 0, 2, and 0, 3 correspond to products 300 and 400 respectively, both divisible by 10. The pairs 1, 2, and 1, 3 give products 600 and 800, and finally, the pair 2, 3 gives 1200. All of these products satisfy the condition of being divisible by 10, so we count all 6 pairs. This example shows how larger values in nums, combined with a smaller k, can result in many valid pairs. Additionally, the constraints remind us that we must consider edge cases carefully, such as arrays with repeated elements or very large values, and ensure our approach is efficient even for the largest inputs. When tackling this problem, one of the first approaches we might consider is the brute force method. Here, we iterate through all possible pairs of indices, I, j, where I is less than j, and check if the product of nums, I, and nums, j, is divisible by k. This approach is simple and intuitive since it directly evaluates the condition for each pair. However, it requires 2 nested loops, resulting in a time complexity of n squared. For small arrays, this might work fine, but when n increases to the problem's upper limit of 100,000, this approach becomes computationally expensive and impractical. Instead, we can optimize the solution by rethinking how we evaluate divisibility. Specifically, we can reduce redundant calculations by leveraging the properties of the greatest common divisor, or GCD, and factorization to narrow down the problem to a more manageable size. This shift in perspective allows us to avoid explicitly iterating through all pairs, making the solution far more efficient. To implement the optimized approach, we start by calculating the GCD of each number in the array with k. We'll refer to this value as g_i for each nums, I. The next step is to use a hash map to track the frequency of each g_i. This information is crucial because it allows us to efficiently count the number of valid pairs for each nums, I, without needing to check every possible combination. For a given nums, I, we determine how many previously seen values have a g_j that can form a valid pair with g_i, such that the product of their GCDs divides k. This approach significantly cuts down on redundant calculations compared to the brute force method. In terms of complexity, calculating the GCD for each number in the array takes O log k, and since this is done for all n elements, the overall complexity is O n asterisk log k. This makes the optimized approach not only feasible but also efficient for the problem's constraints. The key insight that makes this approach so effective is the realization that the divisibility condition can be reduced to a problem involving the GCD and the factors of k. By using a hash map to count the frequencies of these GCDs, we eliminate the need for explicit pairwise calculations, enabling us to count valid pairs in a highly efficient manner. This approach is chosen because it strikes the perfect balance between computational efficiency and scalability. The complexity drops from O n squared in the brute force method to O n asterisk log k, making it well suited for handling the upper limits of the input size. While this optimized approach does require a deeper understanding of mathematical concepts like GCD and factorization, the benefits far outweigh the added complexity in implementation. Compared to alternative methods, such as sorting or direct modulus checks, this solution stands out as the most robust and scalable option. By leveraging these mathematical insights, we address the problem efficiently and ensure the solution performs well under the given constraints. To solve this problem, we need to identify all pairs of indices, I, j, in the array nums such that the product of their corresponding values, nums, I, asterisk nums, j, is divisible by k. This means that the product must be a multiple of k, which can be expressed mathematically as nums, I, asterisk nums, j, %k equals 0. A key insight here is that instead of directly working with the product, we can simplify the problem using remainders. If nums, I, %k equals or 1 and nums, j, %k equals or 2, the condition becomes or 1 asterisk or 2 %k equals 0. This means the remainders or 1 and or 2 must combine in such a way that their product is divisible by k. By focusing on these remainders, we can significantly reduce the computational complexity of the problem. To efficiently count valid pairs, we begin by pre-computing the frequency of remainders when the elements of nums are divided by k. For this, we initialize an array remainder_count of size k, where each index represents a possible remainder, and its value tracks how many numbers produce that remainder. As we iterate through the array nums, we compute the remainder of each number modulo k and increment the corresponding index in remainder_count. Once we have these frequencies, we can calculate the number of valid pairs using three key cases. First, for numbers with a remainder of 0, any two such numbers form a valid pair, and we calculate the count using the combination formula. Second, for other remainders or 1, we find the complementary remainder or 2 equals k, or 1 that satisfies the condition or 1 asterisk or 2 %k equals 0. The count of such pairs is the product of their frequencies. Lastly, if our 1 equals or 2, we again use the combination formula to count valid pairs. Importantly, we ensure no double counting by only considering pairs where our 1 or 2. After evaluating all cases, we sum up the counts of valid pairs and return the total. This process leverages the key insight that working with remainders greatly simplifies the problem. By pre-computing the frequencies of remainders, we eliminate the need to explicitly compare every pair of numbers, which would have been computationally expensive. Instead, we reduce the problem to efficient arithmetic operations on a frequency array. This optimization not only simplifies the implementation but also transforms the computational complexity from quadratic to linear. Additionally, the symmetry of remainders ensures that we don't count the same pair twice, as we always handle complementary remainders systematically. The efficiency of this algorithm can be analyzed in terms of its time and space complexities. Pre-computing the remainders requires a single pass through the array nums, which takes n time. Counting valid pairs involves iterating through the possible remainders, which is an k operation. Therefore, the total time complexity is n plus k. For space complexity, we only require an array of size k to store the remainder frequencies, resulting in a space complexity of k. This is a significant improvement over the naive brute force solution, which has a time complexity of n squared. By leveraging modular arithmetic and pre-computed frequencies, the algorithm achieves a highly efficient solution to the problem. This Python implementation efficiently solves LeetCode problem number 2183, count array pairs divisible by k. ###explanation. 1. Imports and initialization. We start by importing GCD, greatest common divisor, from the math module and counter from collections to manage counts of GCD values. The solution class defines the count pairs function, which takes the input array nums and integer k. Inside the function, we initialize a counter object count to track occurrences of GCD values and a variable result to store the total number of valid pairs. 2. Iterating through the array, for each number in nums, we compute its GCD with k using GCD number k. This GCD represents the largest factor of k that divides the current number, providing a key insight for the divisibility check. 3. Checking pair divisibility. For each existing GCD value, from the count dictionary, we check if the product of the current GCD and the stored GCD is divisible by k. If so, it means all pairs formed between the current number and numbers corresponding to the stored GCD are valid. We increment the result by the frequency of the stored GCD. For updating the counter, after processing potential pairs, we update the count dictionary by incrementing the frequency of the current GCD. 5. Returning the result. Finally, after iterating through all numbers, we return the accumulated result as the total number of valid pairs. ###efficiency. This approach is efficient due to the mathematical insight of using GCD values. Instead of directly iterating through all pairs, n squared, the algorithm leverages a hash map to track GCD frequencies, leading to an average case time complexity closer to n*log k. This makes it well suited for constraints where the input size can be large. Here, we start implementing the solution to count array pairs divisible by k using Java. First, we import the necessary utilities and define the solution class. Within it, we create the count pairs method, which takes an integer array nums and an integer k as arguments. To efficiently calculate the result, we use a hash map called GCD frequency to keep track of the frequency of the greatest common divisors, GCDs, of the numbers in the array with respect to k. We also initialize a variable result to store the count of valid pairs. Next, we iterate over each number in the array. For each number, we calculate its GCD with k using the helper method GCD. Once we have the GCD, we check the map for any previously stored GCDs that, when multiplied with the current GCD, result in a product divisible by k. If such GCDs exist, we add their frequencies to the result. Finally, we update the map to include the frequency of the current GCD, incrementing its count if it already exists. This ensures that all potential GCDs are tracked for subsequent iterations. The implementation of the helper method GCD is shown here. This method calculates the greatest common divisor of two integers using the Euclidean algorithm. The algorithm works by repeatedly replacing the larger number with the remainder of the division of the two numbers, until one of the numbers becomes 0. At that point, the other number is the GCD. In the code, we use a while loop to continue this process as long as b is not 0. Inside the loop, we temporarily store the value of b, then update b to %b, and finally assign the temporary value to a. When the loop ends, we return n as the GCD. This helper method is critical for our main logic, as it ensures we can efficiently calculate the GCDs needed to determine compatible pairs in the array. In this problem, we need to find the number of pairs of indices, I, j, in the array such that the product of their corresponding values, nums, I, *nums, j, is divisible by a given integer k. To solve this, we use the mathematical concept of the greatest common divisor, or GCD, and maintain a hash table to efficiently count how many numbers share certain GCD properties. Let's consider an example where nums equals 2, 3, 4, 6, and k equals 6. Initially, we create an empty hash table called count to store the GCD values and set result to 0 to keep track of the number of valid pairs. For the first number equals 2, we compute the GCD of 2 and 6, which is 2. At this point, we check the hash table for any previously recorded GCDs that can form valid pairs with this GCD underscore number. Since the table is empty, no pairs are added, and we update the hash table to include this GCD, count equals 2, 1. Next, we process the second number equals 3, and calculate its GCD with 6, which is 3. We then check the hash table to see if any previously stored GCDs can combine with GCD underscore number equals 3 to form a product divisible by 6. For the GCD value 2 already in the table, we find that 3 asterisk 2% 6 is not 0, so no valid pairs are added. We update the hash table, count equals 2, 1, 3, 1. Moving on to the third number equals 4, its GCD with 6 is 2. This time, we check the hash table and find that multiplying GCD underscore number equals 2 with one of the existing GCD underscore other equals 2 values gives a product divisible by 6. This adds one valid pair to the result. For GCD underscore other equals 3, the product is not divisible. We update the hash table to count equals 2, 2, 3, 1, and increment result to 1. Finally, for number equals 6, the GCD with 6 is 6. Checking the hash table, we find that 6 asterisk 2% 6 is 0, adding 2 pairs, and 6 asterisk 3% 6 is also 0, adding one more pair. The hash table becomes count equals 2, 2, 3, 1, 6, 1, and the result reaches 4. Thus, the output for this example is 4 valid pairs. Now consider another example where nums equals 10, 15, 20, 25, and k equals 5. As before, we initialize the hash table count and set result to 0. For the first number equals 10, the GCD with 5 is 5. Since the table is empty, no pairs are added, and we update count equals 5, 1. For number equals 15, the GCD is also 5. Checking the hash table, we find one valid pair since 5 asterisk 5% 5 equals 0. The hash table is updated to count equals 5, 2, and the result becomes 1. For number equals 20, the GCD is again 5. This time, there are 2 valid pairs, as there are 2 previous occurrences of GCD underscore number equals 5. We update the hash table to count equals 5, 3, and the result to 3. Finally, for number equals 25, the GCD is still 5. Now there are 3 valid pairs because there are 3 previous occurrences of GCD underscore number equals 5. The hash table becomes count equals 5, 4, and the result is updated to 6. The final output for this example is 6 valid pairs. Lastly, let's look at an example with nums equals 1, 2, 3, 4, and k equals 1. Here, since k equals 1, the GCD of every number with 1 is simply 1. We initialize the hash table and set result to 0. For number equals 1, the GCD is 1, and we update the hash table to count equals 1, 1. For number equals 2, the GCD is again 1, and there is one valid pair with the previous occurrence of GCD underscore number equals 1. The hash table becomes count equals 1, 2, and the result is updated to 1. For number equals 3, the GCD is still 1, and there are now 2 valid pairs, bringing the result to 3. Updating the hash table gives count equals 1, 3. Finally, for number equals 4, the GCD remains 1, and there are 3 valid pairs with the previous occurrences. The hash table becomes count equals 1, 4, and the result is updated to 6. The final result for this example is 6 valid pairs. The key steps in this approach involve calculating the GCD of each number with k, checking for compatibility with previous GCDs in the hash table, and efficiently counting occurrences to avoid redundant computations. This method achieves a time complexity of n*m, where m is the number of unique GCD values. In analyzing the time complexity, we start with the outer loop, which iterates through each element in the array nums. Since nums has n elements, this loop contributes n to the overall time complexity. Inside this loop, we calculate the GCD of the current number in k, which is done using the GCD function. The time complexity of the GCD function is log min number k. In the worst case, this simplifies to log k, because k is a constant and typically larger than most elements in nums. Since the GCD calculation happens once for each element, the total contribution from GCD computations is O, n asterisk log, k. Now, for every number in the array, the algorithm checks previously encountered GCD values stored in the count dictionary. This involves iterating over all the dictionary keys, which represent unique GCD values. If there are m unique GCD values, the inner loop runs O, m, times. During each iteration, it evaluates whether the product of two GCD values is divisible by k. This condition check is a constant time operation, O1. In the worst case, the number of unique GCD values can be as large as the number of divisors of k, which is O, k. Therefore, the inner loop contributes O, n asterisk m, to the total complexity, which becomes O, n asterisk k, in the worst case. Combining all these contributions, the time complexity ranges from O, n asterisk log, k, in the best case, where m is small, to O, n asterisk k, in the worst case, where k has many divisors. Turning to space complexity, the dominant factor is the count dictionary. This dictionary stores the frequency of unique GCD values encountered during the computation. In the best case, where k has very few divisors, the size of the dictionary is minimal. However, in the worst case, the number of unique GCD values can equal the number of divisors of k. The number of divisors is at most O, sqrt, k, because divisors come in pairs, but for simplicity, we approximate this as O, k, in the worst case. Beyond the dictionary, only a few auxiliary variables like result, GCD underscore number, and loop variables are used, which require constant space, O1. Combining these, the overall space complexity ranges from O1 in the best case to O, k, in the worst case. To put this into perspective, let's compare the current solution with a brute force approach. In a brute force method, we would check all possible pairs, I, j, where I less than j to see if the product of nums, I, and nums, j, is divisible by k. This involves O, n squared, pairs, and since the divisibility check is O1, the total time complexity is O, n squared. The space complexity of the brute force approach is O1, as it doesn't use additional data structures. In contrast, the optimized solution avoids checking all pairs by leveraging the properties of GCD and divisors. It uses a dictionary to store and reuse information about previously seen GCD values, significantly reducing the number of checks. This brings the time complexity down to O, n asterisk log, k, in the best case and O, n asterisk k, in the worst case, with a space complexity of O, k. In conclusion, the current solution demonstrates a significant improvement in efficiency over the brute force approach, particularly for large arrays or when k has a small number of divisors. The outer loop runs O, n, times, the GCD calculation contributes up to O, log, k, per iteration, and the inner loop iterates over up to O, k, unique GCD values in the worst case. Combining these factors, the overall time complexity simplifies to O, n asterisk k, in the worst case. The space complexity, dominated by the count dictionary, is at most O, k. This optimized approach leverages mathematical properties to achieve much faster performance, making it well-suited for larger input sizes. In this section, we address some common mistakes to watch out for when solving this problem. First, it's crucial to handle edge cases properly. For example, if k is 0, a direct modulus operation will throw an error, so you need to validate the inputs beforehand and handle such cases explicitly. Similarly, when k is negative, you should account for how that affects your logic. Next, skipping pre-processing for efficiency is another frequent oversight. Instead of directly iterating over all pairs, you can pre-process the array by storing the frequency of remainders when dividing elements by k. This simplifies subsequent calculations and avoids redundant operations. Another pitfall is misunderstanding modulo logic. Remember that the distributive property doesn't always hold for modulus. For example, a asterisk b percent k is not necessarily equal to a percent k asterisk b percent k. Finally, in languages like Java or C++, integer overflow can occur when multiplying large numbers. To prevent this, you should use modular arithmetic or switch to data types like long that can accommodate larger values. Now, let's consider the issue of brute force approaches. While a straightforward solution might involve iterating over all possible pairs, this results in an O, n squared, time complexity and is impractical for large inputs, such as when n is 10,000. Instead, focus on optimizing your solution. Modular arithmetic is often key to solving divisible pair problems. For instance, if an element has a remainder x when divided by k, the complement needed for divisibility can often be derived as kx%k. Pre-processing the array to count occurrences of each remainder, using a hash map or frequency array, can reduce the problem to linear time complexity. It's also important to test your solution against diverse edge cases, such as arrays with a single element repeated, very small arrays, or large values of k. Additionally, be ready to discuss space-time trade-offs, as optimized approaches often require extra space to store frequencies. Finally, studying related problems like LeetCode 1010, 974, or 1497 will help you recognize recurring patterns and apply similar techniques effectively. There are also alternative approaches you might explore depending on the constraints. One powerful method is using a hash map to store the frequency of remainders when dividing elements by k. This allows you to efficiently calculate the number of valid pairs by analyzing these frequencies, with a time complexity of O, n, and space complexity of O, k. Another option is the two-pointer technique, which works well for sorted arrays. By sorting the array first, you can use two pointers to identify pairs that satisfy the given conditions. This approach is particularly useful when additional constraints, such as a maximum difference between elements, are introduced. However, it does involve an O, n log n, complexity due to sorting. Finally, for smaller inputs, you might consider an optimized brute force approach. While still O, n squared, you can speed up the process by implementing early exits when conditions are met. This makes brute force more practical for small-scale problems, even if it remains computationally expensive for larger arrays. Great work on completing this problem. To recap, we explored various approaches, focusing on efficiency and optimization. Remember the key techniques we discussed, and continue honing your problem-solving skills. Thank you for watching, and don't forget to like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!